This project was a team effort as it was led by Khairul Nazhan. Followed by our brilliant co-author were Ilya, Sophia, and Hazlin, and also our supervisors were Dr. Natsira and Dr. Ward. Across our cities, beneath the very foundations of our civilization, a silent war is being waged. It's not fought with armies, but with time, weather, and the relentless advance of corrosion. It's an insidious enemy that strikes at the heart of our infrastructure, causing concrete to crack and steel to crumble. We lose billions each year to this underlying decay. But what if we could build a shield so powerful, so effective, that this threat could be rendered obsolete? Hence, our research presents an answer, not through radical new materials, but through a brilliant synergy of old and new. We had a clear objective to develop a high-performance blended mortar that acts as a superior protective shield against corrosion. The first is Ground Granulated Blast-furnace Slag, a remarkable byproduct of industry. When blended with cement, it creates a denser, more protective mortar. It's our sustainable foundation. But our secret weapon lies in the nanoscale additive called as graphene oxide. Graphene oxide, or known as Ggbs, is a two-dimensional, single-atom-thick layer of carbon atoms with oxygen functional groups derived from the chemical oxidation of graphite. It's easily dispersed in water due to oxygen functional groups, creating a homogeneous mixture with the cement matrix. The molecular of graphene oxide fundamentally changes the cementitious microstructure through three key mechanisms. The filling effect reduces the amount of voids in the cement matrix. Meanwhile, the bonding effect tends to increase the cohesive mechanism during mixing, creating homogeneous mixtures. Lastly, the nucleation effect facilitates the hydration process to form and grow the strength of the mortar. To turn theory into reality, our journey led us to the lab. Our preparation process was a precise sequence. We first dry mixed the OPC and sand with the Ggbs. Next, we added water and continued to mix. The final ingredient, our star player, was the graphene oxide Ggbs, which was carefully introduced and mixed thoroughly. This blended material was then cast into molds, compacted to remove any air voids, and left to cure, creating our mortar specimens for testing. We then subjected them to two crucial challenges: the rapid chloride permeability test, the ultimate stress test for durability, and the compressive strength test to ensure our shield was not only protective but structurally sound. Based on the provided information, a small amount of graphene oxide 0.02% works perfectly, making the concrete stronger and denser. On the other hand, using too much 0.04% or more causes the graphene to clump together, which weakens the concrete instead. Similar with the compressive strength, adding a tiny amount of graphene oxide 0.02% makes the concrete denser by filling tiny holes. This makes it much harder for things like salt to get through, which protects it from damage. This finding highlights that the addition of 0.02% Ggbs effectively refines the internal microstructure of and gives a superior compressive strength is also responsible for a refined pore structure, making it highly resistant to the penetration of chloride ion. This technology promises to extend the service life of concrete infrastructure by decades, drastically reducing the need for costly and time-consuming repairs. By using Ggbs blended mortar from the outset, we can build a more resilient infrastructure, ensuring the safety of our bridges, buildings, and roads for future generations. Of course, a project of this nature is not without its hurdles. Graphene oxide has a tendency to clump together, which would compromise its effectiveness. But the difficulties didn't stop there, as it comes at a significant cost. We needed to find the sweet spot where we could achieve maximum corrosion protection and strength without making the product prohibitively expensive. While our findings are promising, our work is not yet complete. Future research will focus on several key areas to improve our product. We need to conduct long-term exposure go tests to fully understand the durability over time, find the perfect balance between performance and cost. Additionally, our work directly addresses the global challenges outlined in the UN's Sustainable Development Goals, aligning with SDG 12, Responsible Consumption and Production, and SDG 9, Industry, Innovation, and Infrastructure. We're not building a stronger concrete, but we're building foundations for a sustainable and resilient world.